Hello students, welcome back to this lecture 1 Real Numbers. So in this lecture we will discuss about the fundamental theorem of arithmetic. Okay, and then we'll discuss some examples of fundamental theorem of arithmetic, and then we'll give an important note on this theorem. Okay, so the fundamental theorem of arithmetic. So in our previous class, we actually introduced the fundamental theorem of arithmetic. Okay, so fundamental theorem of arithmetic is an important and crucial theorem to study integers. Okay, so it's stated to us every composite number. So you all know about composite number. Okay, so composite number is nothing but a number which have more than two divisors other than one and itself. Okay, so every composite number can be expressed or factorized as a product of primes. Okay, and this factorization is unique apart from the order in which the prime factors occur. Okay, so for example, you can take this number 20. Okay, so 20. So by using factors tree, we can find its factors. Okay, prime factors basically. So here 20 is divisible by 2. So the divisors of 20 are 2 and 10. And further, the divisors of 10 are the prime divisors of 10 are 2 and 5. Okay, so the factorization of 20, so we have factorized 20 as 2 into 2 into 5. Okay, and this is equal to 2 square into 5. So here 20 is a composite number, and this number can be expressed as a product of prime numbers, that is 2 into 2 into 5, that is 2 square into 5. Okay, where 2 square and 2 and 5 are prime factors of 20. Okay, so 20 can be factorized as 2 square into 5. Okay, now so that is given any composite number, there is one and only one way to write it as a product of primes, as long as we are not particular about the order in which the primes occurs. Okay, so here any composite number, okay, we can write any composite number in only one and unique way to write it as a product of primes. Okay, but we are not particular about the order in which primes occur. Okay, so for example, we regard 2 into 3 into 5 into 7, this prime factorization, and 3 into 5 into 7 into 2, this prime factorization, they are same. Okay, so or any other possible order in which these primes are written. Okay, so we are not particular about the order in which the primes occur. Okay, so in general, given a composite number x, so suppose we have given a composite number x and we factorize it as x is equal to p1 into p2 into p3 into pn. Okay, so here composite number x, that is x for x there are more than two divisors which are divisible, which divides the x. Okay, so if we factorize x as p1 into p2 into p3 into pn, where p1 p2 pn are primes, okay, and written in ascending order, that is p1 less than equal to p2 less than equal to less than equal to pn. So if we combine the same primes, we'll get powers of primes. Okay. So for example, 32760. So we have already seen the prime factorization of 32760. Okay. So the prime factorization of 32760 is 2 into 2 into 2, 3 into 3 into 5 into 7 into 13. Okay. So this can be written as 2 to the power 3 into 3 to the power 2 into 5 into 7 into 30. Okay. So once we have decided that the order will be ascending, then the way the number is factorization is unique. Okay. So when we have decided that the order will be ascending order. Okay. Then that case, the way of the number is factorized in unique way. Okay. So basically, in general, if we have a given number, composite number given, okay, and x can be written as p1 into p2 into p3 into dot pn. Okay, where p1, p2, p3 dot pn are primes number and written in ascending order. That is, p1 is less than equal to p2, less than equal to p3, less than equal to p4, and less than equal to dot pn. Okay, so if we combine the same primes and we'll get powers of primes. Okay, we can do this. Okay, combine the same primes, we'll get powers of primes. So this number 32760, this can be written as 2 cube into 3 square into 5 into 7 into 30. And this way of factorization is a unique way. Okay. So now we'll discuss example. So we consider the numbers 4 to the power n. Okay, so here we consider number 4 to the power n, where what is n? Where n is a natural number. So you have known about natural number. So natural number basically we use for counting, like 1, 2, 3, 4, 5, 6, 7, 8. So these are all natural numbers. So we here consider the numbers 4 to the power n, where n is a natural number. And here we have to check whether there is any value of n for which 4 to the power n ends with the digit 0. So here we have to check whether there is any value of n for which 4 to the power n ends with the digit 0. That is 4 to the power n. Suppose here will be some value and and ends with 0. Is it possible? So we know if a number ends with 0, then that number must divisible by 10 and 5 and 2. Okay. So if the number 4 to the power n for any n were to end with digit 0, then it would be divisible by 5. Okay. That is, the prime factorization of 4 to the power n would contain the prime p. Okay, so the prime factorization of 4 to the power n would contain the prime m, prime p, prime m. Okay, would contain the prime 5. Okay, so this is not possible because 4 to the power n, this can be written as 2 to the power 2n. Okay, and so the only prime in the factorization of 4 to the power n is 2. So the uniqueness of the fundamental theorem of arithmetic guarantees that there are no other primes in the factorization of 4 to the power n. So there is no natural number n. Okay, so for which 4 to the power n ends with the digit 0. So there is no natural number for which 4 to the power n ends with the digit 0. Okay. Similarly, you can check for 6 to the power n. Okay. So if you consider 6 to the power n, sub 6 to the power n a composite number. Okay, and whether check whether there is any natural number n for which 6 to the power n ends with 0. Okay, so you can factorize 6 to the power n as 2 into 3 whole to the power n. Okay, but if the number 6 to the power n for any n were to end with the digit 0, then it would be divisible by 5. Okay, it would be divisible by 5. But in factorization of 6 to the power n would not contain 5. Okay, so would not contain 5. So this is not, because 6 to the power n is equal to 2 into 3 whole to the power n. Okay, and the uniqueness of the fundamental theorem of arithmetic guarantees to us that there is no other primes in the factorization of 6 to the power n. Okay, so there is no natural number in for which 4 to the power n ends with the digit 0. Okay, let us move to another example. So you have already learned how to find the HCF and LCM of two positive integers using the fundamental theorem of arithmetic in earlier classes. Okay, so without realizing it, the method is also called prime factorization method. Let us recall this method. Okay, so here we first define what does mean LCM of two positive integers. So the least common multiple of two numbers is the smallest number that is a multiple of both. Okay, suppose you have two numbers 4 and 5. Okay, so the multiples of 4 are 4, 8, 12, 16, 20, 24, 28 and dot. Okay, and the multiples of 5 are 5, 10, 15, 20, 25, 20, 30, 35 and dot. So here 4 is not common in both, 8 does not common in both, 12 does not common in both, 16 does not common in both, 20. So this number 20 and this number 20, so they are common in both set of multiples of 4 and 5. Okay, so 20 here, the smallest number, that is a multiple of 4 and 5. Okay, so LCM of 4 comma 5, this is equal to 20. Okay, so LCM of two numbers. So to find the LCM of two numbers, you list the prime factors of each number, and then for each different prime numbers, you take the highest power of that prime numbers from either number and multiply them together. Okay, so what does mean by LCM? So LCM is basically product of the greatest power of each prime factor. Okay, so product of the greatest power of each prime factors involved in the number, that is called LCM, or least common multiples of a number. Okay, now for example, to find LCM of 12 and 15. Okay, so here we have to find the LCM of 12 and 15. So first we will find the LCM of 12 and 15 by in general method. Okay, so first we will find the multiples of 12. So multiples of 12. So multiples of 12 are 12, 24, 36, 48, 60, 72 and dot. Okay, and the multiples of 15 are 15, 30, 45, comma 60, comma dot dot dot. Okay, so here you can see 60, this number, these multiples. Okay, the common multiples of 12 and 15 are 60 and so on. Okay, so here the smallest common multiple, smallest common multiples, multiple of 12 and 15 is 20. Okay, so therefore the LCM is 60. Okay, so the LCM of 12 comma 15 is equal to 60. Okay, so this is our basic definition of LCM, least common multiples. Okay, so now if we use factorization method for finding the LCM of 12 and 15, so that case first we have to factorize 12. Okay, so the factorization of 12 basically is 2 square into 3. Okay, so 12 can be written 2 square into 3, and the prime factors of 15 is basically 3 into 5. Okay, so now the LCM will have the highest power of one prime numbers present. Okay, so which gives us 2 square into 3 into 5. Okay, and this is equal to 60. So LCM is basically the product of highest power of prime factors in present in number. Present of numbers. Okay, so LCM basically the highest product of highest power of the prime factors that is present in two numbers. Okay, so the LCM of 12 and 15 is 60. Okay, so now we'll define highest common factor. Okay, so first, what is factor? So we already discussed about factors. Okay, so suppose you have 20 numbers. Okay, so the factors are maybe 2 and 10, and the factors of 10 are 2 and 5. So the factors of 20 are 2, 5, 10 and 20. Okay, so these are all factors of 20. Okay, so for highest common factor, so by this name suggests that we need to take highest common factor of two numbers. Okay, so highest common factors, also known as the greatest common divisors or GCD of two numbers. Okay, and is the largest number that divides both of them without leaving a remainder. Okay, so to find the HCF of two numbers, you list the prime factors of each. Okay, and then take the lowest power of all prime numbers that appear in both lists. Okay, so HCF is what? So HCF is basically product of the smallest power of each common prime factor in the numbers. Okay, in the numbers. So basically prime numbers, what is prime numbers? So if we have two numbers, A is equal to 4 and B is equal to 6. Okay, then the factors of 4, what? 1 prime factors, basically the prime factors of 1, 2, 4. These are factors of 4. Okay, and the factors of 6 are 1, 2, 3 and 6. Among them, which factor is common in both? So among them, 1 and 2 common in both. Okay, so here highest common factor is 2. So HCF of 4, 6 is equal to 2. Okay, by prime factorization method, HCF is basically product of the smallest power of each common prime factors in the numbers. Okay, so for example, we need to find the HCF of 12 and 15. Okay, so student, we already know the prime factors of 12, that is 2 square into 3. Okay, so the prime factors of 12 is 2 square into 3, and the prime factors of 15 is 3 into 5. Okay, so here in both prime factorization of 12 and 15, here the common prime factor is 3. Okay, so the here common prime factor is 3. So both the numbers have the prime factor 3 in common. So the HCF of 12 and 15 is 3. Okay, so HCF is basically HCF of 12, 15. This is basically equal to the product of lowest power of common prime factors in the numbers. Okay, so HCF of 12, 15, this is equal to the lowest power of the common factor is 3. Okay, 3 to the 1. So HCF of 12, 15, this is equal to 3. Okay, so the HCF of 12, 15 is equal to 3. So now let us find the LCF and HCF of 6 and 20. Okay, by the prime factorization method. So without using prime factorization method, we can easily find its LCM and HCF also. Okay, so but here we use prime factorization method for finding the LCM and HCF of 6 and 20. Okay, so here the prime factors of 6 is 2 to the power 1 into 3 to the power 1. Okay, and the prime factors of 20 is 2 into 2 into 5, that is equal to 2 square into 5 to the power 1. Okay, and we know the HCF of two numbers is basically the product of prime factors, which is lowest power of the common prime factors. Okay, so here HCF, this is equal to HCF of 6, 20. This is actually the common lowest power of the common product of lowest power of the common prime factors. Okay, so here the common prime factors are 2 in both numbers. Okay, so HCF of 6, 20, this is equal to 2, and LCM of 6, 20, that is actually the product of highest power of the common factors in both numbers. Okay, so here the highest power of the prime factor 2 is 2. Okay, so 2 square into the highest power of 3 is 1, so into 3, and into highest power of 5 is 1, so into 5, and if we multiply them, then we'll get this is equal to 60. So LCM of 60, 6, 20, this is equal to 60. Okay, so note that HCF of 6, 20, this is equal to 2 to the power 1. Okay, and this is equal to product of the smallest power of each common prime factors in the numbers. Okay, and LCM of 6, 20, this is equal to 2 square into 3 to the power 1 into 5 to the power 1, and this is basically equal to product of the greatest power of each prime factor involved in the both numbers. Okay, now from the example above, you might have noticed that HCF of two numbers 6, 20, this is, if we take this and LCM of 6, 20, if we take, then if we multiply them, HCF of 6, 20 into LCM of 6, 20, then this basically will give us the product of two numbers, 6 into 20. Okay, so in fact, we can verify that for any two positive integers, a and b, for any positive two integers, a and b, HCF of a comma b into LCM of a comma b, this is equal to a into b. Okay, so HCF of AB into LCM of AB, this is equal to product of two numbers. So we can use this result to find the LCM of two positive integers if we have already found the HCF of two numbers, two positive integers. Okay. So now take this example. So find the HCF of 96 and 404 by the prime factorization method, and hence find their LCM. Okay, so first find HCF of these two numbers. So first we have to factorize 96, and if we factorize 96, then we will get this is equal to 2 to the power 5 into 3. Okay, and the factorization of 404, this is equal to 2 square into 101. Okay, and therefore the HCF of these two numbers is basically the product of the lowest power of common factors, prime factors in both numbers. Okay, so therefore the HCF of these two numbers is the lowest power common prime factor is 2. Okay, and the lowest power of 2 is 2. Okay, so the HCF of two positive integers is 2 square, that is equal to 4. Okay, and we also know this formula, HCF of a comma b into LCM of a comma b, this is equal to a times b. Okay, so HCF of two numbers into LCM of two numbers, this is equal to product of two numbers. Okay, so we already found HCF of 96 comma 404, this is equal to 4. Okay, so now HCF, that is 4 into LCM of a comma b, this is equal to 96 into 404. Okay, and it implies LCM of 96 comma 404, 96 comma 404, this is equal to 96 into 404 divided by 4, and it is equal to 9696. Okay, so LCM of 96 comma 404 is equal to 9696. Okay, and next example, here find the HCF and LCM of 6 comma 72 and 120 using the prime factorization method. Okay, so the first we have the prime factorization of 6 is 2 into 3, and the prime factorization of 72 is equal to 2 to the power 3 into 3 square, and the prime factorization of 120 is equal to 2 to the power 3 into 3 into 5. Okay, and here 2 to the power 1 and 3 to the power 1 are the smallest powers of the common factors of 2 and 3 respectively. So the HCF of 72, 6 comma 72 comma 120, this is equal to 2 to the power 1 times 3 to the power 1, and this is equal to 2 into 3, this is equal to 6. Okay, now here the 2 to the power 3, 3 to the power 2 and 5 to the power 1 are the greatest power of the prime factors 2, 3 and 5 respectively. Okay, involving the three numbers. So the LCM of 6 comma 72 comma 120, this is equal to 2 to the power 3 into 3 to the power 2 into 5 to the power 1, and this is equal to 360. Okay, and here remark that, notice, if we multiply these three numbers 6, 72 and 120, so 6 into 72 into 120, this does not equal to HCF of 6 comma 72 comma 120 into LCM of 6 comma 72 into 6 comma 72 comma 120. So the product of three numbers is not equal the product of their HCF and LCM. Okay. But in case of two numbers, two positive integers, the product of two numbers is equal to HCF of two numbers into LCM of two numbers. Okay. But for three numbers, the product of three numbers does not equal to the product of their LCM and HCF. Okay. So student, I stop here this lecture. So thank you very much to all of you.